Hi folks, welcome back to Physics with Captain Rod. I'm making this video here to get you started on numbers 7, 11, and 13 in Chapter 18 in your OER College Physics text. So let's chat about number 7. Let's see, it says a 50-gram ball of copper has a net charge of 2 microcoulombs. So I'm going to start with a little picture. Here's my ball of copper. It's got a mass of 50 grams. Net charge is given. Of 2 microcoulombs, 2.00 microcoulombs. Now remember, micro, this means 10 to the minus 6 coulombs. And it says, let's see, what fraction of the copper's electrons have been removed. So, first of all, let's chat about how I knew this thing was positively charged. Copper's a metal, and the defining characteristic of a metal is that metals have just a couple of 1 or 2 outer shell electrons that are very easy to remove. So anytime they become ionized, they become positively charged because it's always a removal of electrons when you're charging a metal like copper. Now, let's start with this. The charge is given right here. And remember how you charge something. Like if I remove 1 electron, imagine me, taking some tweezers here and grabbing an electron, so to speak, and pulling it off. Then the charge would be 1.6 times 10 to the minus 19th coulombs on this object, positive. If I take my tweezers, remove another one, the charge on this object would be 2 times this. If I remove another one, it'll be 3 times this value, and so forth. Whatever this charge is, it has to be some integer value times 1.6 times 10 to the minus 19th coulombs. So the charge is given in the problem. This is going to allow you to calculate n, how many electrons are actually lost. Okay. Now, the question asks for what fraction of the electrons are gone. So in order to know that, we need to know, I'll put n sub t here, the total number of electrons. Well, let's start with this 50 grams. If you get a periodic table, there is a number on that table that has units of grams per mole. It's called the molar mass. You're going to have to look that up unless it's actually given in the problem. Nope. So you're going to look up the molar mass of copper, and again, that's going to be a number, and it's going to have units of grams per mole. What you're going to do is you're going to take this 50 grams, you're going to use this to convert it to moles. Now, remember that a mole is Avogadro's number of particles. Avogadro's number is 6.022 times 10 to the 23rd. It's either atoms or molecules depending on what you're talking about. Here we're talking about copper, so the appropriate thing would be to say atoms. Okay. So after you convert this to moles, use this to calculate the number of atoms. And then in the problem, it says each copper atom has 29 protons. That's called the atomic number, usually written with the letter Z. And a stereotypical atom has the same number of protons as it does electrons. So because it has 29 protons, we can assume it starts with 29 electrons. So once you have the total number of atoms, times 29 will give you the total number of electrons, and then you can compare that to this value. Take the n which was removed, divide it by the total number of electrons, you will get a decimal. If you want to then multiply by 100, that'll convert it to a percent. That should be enough for number 7. Quite a bit of chemistry there in number 7, huh? Alright, let's talk about number 11. How strong is the attractive force between a glass rod with a charge of 0.7 microcoulombs and a silk cloth with a charge of minus 6 microcoulombs, 12 centimeters apart, assuming they act like point charges? So, again, because it says assuming they're like point charges, I'm going to go ahead and just draw a pair of point charges. The values for the charges are given in the problem. Now remember that that micro, this symbol right here, this means 10 to the minus 6. Distance between them, I like to label that with an R, given in the problem. So we're going to get an attractive force between them. I'm going to go ahead and draw force vectors here. And again, that's what we call the Coulomb force. And here's how the Coulomb force is calculated. Where this guy here is the Coulomb constant, 9 times 10 to the 9th Newton meter squared per Coulomb squared. The two charges given in the problem, the distance given in the problem. Be a little cautious because that distance was given in centimeters, but the Coulomb constant is written typically with units of meters, so you're going to want to convert that to meters before you wash that through that equation. What else did they ask here? Discuss how the answer to this problem might be affected if the charges are distributed over some area and do not act like point charges. So what they're saying basically is, imagine this, and imagine that rather than a point charge, maybe it's more like what we call charge distribution. So imagine maybe this charge spread out over maybe a line or something, and same thing over here. Putting it right through the equation here. And then just ask yourself, do you think that this force between these two things would increase, decrease, or be about the same? And give a reason. All right? That should be enough for that guy right there. So we got 2 of these knocked off. All right, we'll start talking about 13 here. So 13, it says 2 point charges are brought closer together, increasing the force between them by a factor of 25. So we got 2 point charges. It didn't really say plus or minus. I'm just going to assume plus plus. Now, if it's plus plus, there would be a repulsive force. And again, that's what we call the Coulomb force. And that force is going to equal K Q1 Q2 over some distance squared. Now, in part 2, they're brought closer together. So I'm going to change my picture. The force would therefore increase. And let me put it like an R1 on this one, where this is R1. And we have a new R that I'm going to call R2. Now if I write Coulomb's law for the second case here, this force is going to equal K Q1 Q2 over R2 squared. And it says that the new force is 25 times the old force. And what that'll allow us to do is write a quick equation here. Set this equal to 25 times this. And what will happen is the K's and the Q's will all divide out, and you'll get an equation here you can between R2 and R1. Right, that should be enough on number 13. So, hope this video helps get you rolling. I'm going to stop this here and just start a new one here on the next 3 problems. Right, have a great day.